Okay, so on Tuesday we started looking at systems of linear inequalities. So when we graph two linear equalities and then find the solution set for them. And we're going to hop right into the example that we didn't do. So just the page after we started, we're going to solve this system. So we have our set notation of x, y, and such that y is greater than or equal to 1, and x is all whole numbers and y is all whole numbers, and then such that y is less than or equal to negative 3x plus 6, and again we're working with all whole numbers. And so we'll remember that all whole numbers are positive numbers, but 0 is also included. So let's look at the information that we're told here. For the first inequality, we know that our boundary is y equals 1. And we know what kind of line it is from the sign, so we know that this is a solid line. And we know that we want all whole numbers, so that we will be only in which quadrant? If we want to be positive in the x and positive in the y, we'll only be in quadrant 1. And then over here, we know that our boundary is y equals negative 3x plus 6. Again, the sign tells us that this is a solid line. And once again, our whole numbers tell us that we'll be working in quadrant 1. So if we then go, and when we say we'll be restricted or working in quadrant 1, those are for the solutions. So when we graph our line, so let's first graph y equals 1 for our boundary. And since we have no slope, it will be a flat horizontal line, so we'll go up 1 on the y-intercept, and we'll draw our solid line. Okay, and then if we look, it says y is greater than or equal to, so it will be everything above that line. Okay, so I'll just put in these little hatching marks for now till we see where our solution set is. And then our second line, our second boundary line is y equals negative 3x plus 6. So our y-intercept is 6, so I'm going to go up to 6. And our slope is negative 3, so it will be down 3 and to the right 1. So down 3 over 1, down 3 over 1. And then we can go up the same. So over 1, up 3. And we can draw our line. Okay, and then for this one, if we look at our inequality, it's everything, so y is less than or equal to. So our boundary there will be below the line. Okay, so again, we'll put just our hatching in. And then we're going to look for the part where they overlap, and that will be our solution set. And we remember that it has to be positive numbers because we're in all whole numbers. So even though they overlap a little bit in this area, that doesn't count because, in this whole, in all these quadrants, they overlap. But we can't consider that part of the solution set because those are negative numbers. So our solution set ends up being this little triangle right here. Okay, so you can see it's just this part, and that is our solution set. Okay, so that's graphing systems of two linear inequalities. If we go on, we can see that if we look at graphs of systems of linear inequalities, we can determine information about the domain and range. And so we can find restrictions. So if we look at this, so this is two inequalities graphed. We have y less than or equal to 2 over 3x minus 3, and y is less than negative 2 over 3x. And so right away I'll know that this one is my dashed line because it's just less than, and that makes this guy my solid line. My solution set is already filled in. It's all this part that's been shaded. And so we can say that the solution set includes, so what kind of values of x and y are included? So I can see that there's positive values of x because we go down that way, over that way, and then there's also negative values of x over here. And if I look at the y, there are just a few positive values of y and lots of negative values of y. So our solution includes positive and negative values of x and y. And then what does this tell us? If it includes positive and negative values, what will our restrictions be? Or will we have any? So if I have x belongs to and y belongs to, what am I going to put here? If it's got positive and negative numbers. And it's continuous because it's all shaded in, it's not stippled. So it will be x belongs to all real numbers and y belongs to all real numbers. And this will be our domain and our range. Okay, so just by looking at the graphed system of inequalities without knowing the restrictions, from what we know now about continuous and discrete data, from what we know about rational numbers and when they're broken into integers, whole numbers, natural or real numbers, we can we can determine our domain and range just based on looking at this system. So right now in the textbook, I'm going to get you to work on questions from page 307, and then also the worksheet 6.2, the one on systems, so the one with graphs on it. I will not be collecting this, okay? On Tuesday, actually I will post the key, so not being collected. So I'll post the key. So try it and then check your answers. I will also post a scan of the textbook questions for those of you who don't have textbooks yet, but remember to get your textbooks on, what is it, on Tuesday. Okay, and then, so you can work on that. You can come back to the video, or we're just going to move on to finish this package of notes. So on real world problems. And so I was talking about this a little bit in class, but lots of real world problems can be shown or modeled by using a system of linear equations. And usually the problem set is restricted to the first quadrant, sometimes the first and second. And this is because we need to be using usually whole numbers, and sometimes integers if we're working with money, but usually whole numbers, right? So people or plates of food or cars or something, and we can't have negatives of those. So here's an example. A company makes two types of boats on different assembly lines: aluminum fishing boats and fiberglass boats. When both assembly lines are running at full capacity, a maximum of 20 boats can be made a day. The demand for fiberglass boats is greater than the demand for aluminum boats, so the company makes at least 5 more fiberglass boats than aluminum boats each day. So when we see this here, that they're making 2 types of boats, we know that we will have 2 variables. So one variable being aluminum boats and one being fiberglass boats. And we're told basically 2 statements, and these 2 statements will be our inequalities. So statement 1 being that they can make 20 maximum a day. And statement 2 being that they make 5 more fiberglass boats than aluminum boats. So let's determine the variables. And so in this case, normally we use X and Y, but when we're working with a real world problem, we can assign them variables that, you know, are more related. So we can say, let A represent the number of aluminum boats, so A for aluminum. And then we'll let F represent the number of fiberglass boats. And we have to, then we can write our linear inequalities, but first we should identify our restrictions. So when we work with our restrictions for A, so we'll have A such that and F such that. And so these are boats. So we can't go negative boats and we can't go decimal boats. We could go 0 boats, right? So they could make 0 aluminum boats a day. That's fine because we just know it's a maximum of 20. And so we're going to say that this is A belongs to all whole numbers and F belongs to all whole numbers. And this is because we can't have negative boats or decimal. So just in general, we can have a negative amount of boats or decimal boats. So on the assembly line, they can't make, you know, 0.3333 of a boat. It has to be either a whole boat or no boat at all. So then let's write our restrictions. So restriction 1 is that they make a maximum of 20 boats a day. Okay, so if we have 20, what kind of inequality will we put here? Less than, greater than, less than or equal to, or greater than or equal to. And so if we have a maximum, we're going to put a less than or equal to sign, because we cannot have more than 20 boats. We can have exactly 20 boats, which is why we put equal to, but we can't have more than. And then it will just be A plus F. So aluminum plus fiberglass boats has to be less than or equal to 20. So this shows us a maximum. And then our second inequality, so remember that we have that the company makes at least 5 more fiberglass boats than aluminum boats each day. So if we have fiberglass boats, and over here, on one side of the inequality, over here we'll have aluminum plus 5, right? So however many aluminum boats they make 5 more fiberglass boats. So then what's our restriction or our inequality going to be? So are there going to be more fiberglass boats or more aluminum boats? There'll be more fiberglass boats. So put a greater than and an equal to, because it's at least. So they could make more than 5, so they could make more than 5 extra boats of fiberglass, but they have to make at least 5. And then we can graph that. And first, to graph it, we have to put our inequalities into y-intercept form. So F greater than or equal to A plus 5 is already in y-intercept form. Okay, or sorry, slope-intercept form. So we have y equals mx plus b. And in this case, F is y, A is x, and so our slope here is 1. Okay, and then our other one, A plus F, less than or equal to 20, we have to get f by itself. So we have f is greater than or equal to, and I'm just going to put the a in front of the 20 right away, so that again we can have our slope. And so here our slope is -1. Okay, and we also have to think about our restrictions. So for restrictions, we have a such that and f such that. And what kind of restrictions will we have on boats? So it'll be the same as before, and it will be all whole numbers, right? Because we can't have negative or decimal, and that's what we wrote up on the page before. And then because we can't have decimal, we have to have what kind of data? So this will be in quadrant 1. And because we have to have whole boats, we can't have decimals or fractions, we have to stipple the boundaries and the solution set. Okay, because it's continuous, so you can't have part of a boat, so it has to be stippled. So on our graph, since we're only working in quadrant 1, I'm just going to only draw us quadrant 1. Okay, and so we'll go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and I'll go up to 20 because that's the maximum we can have. Over here will be our F, so our number of fiberglass boats, right? Because this is our y-axis, and we determine that we set F as y. And then down here is our number of aluminum boats. I don't know why I can't spell boats today. So same thing, 1, 2, 3, 4, 5. And we'll go up to 20 again. Okay, and then let's plot our line. So if we do f is greater than or equal to 5, so we'll go up to 5, that's our y-intercept. We're going to staple this, and it's a 1/1 slope. So I'm going to stipple this up. I'm not going to go the other direction because we can't have negative numbers. And I'll go up here, past 20. And then our other one is f is less than or equal to -a plus 20. And since it's less than or equal to and greater than or equal to, I've put solid dots, not open dots, because of the inequality we were given. So we'll start at 20, that's our y-intercept, and we'll go down a slope of 1. Okay, so I'll keep going down. And then we look to see where it overlaps, and it's this triangle part here. So you fill in your dots, and just do this really quickly. Don't join your dots at all. So all of this part should be filled in. Like that. And if you wanted to, you could test some points to verify your solution. If we go down here, the solution set is the specific points where the regions. So the solutions of each inequality, the solution regions overlap. Okay, and possible solutions are combination of points of A and F in the solution. So if we just pick, let's pick 2 points in here. Oh. So let's pick, how about this point here? So let's pick 2, 12. So that point, and that's 2, 12. And then let's pick 14, 4. Oh, sorry, 4, 14. So on the x-axis over 4 and then up 14. So let's see example sorry, I don't know why I keep saying that. 4, 14 as a solution. So 4, 14 is a possible solution. And let's verify that. So we verify by just filling it in. So for equation 1, we'll put, remember that our first inequality is A plus F is greater, or sorry, less than or equal to 20. So A plus F is greater than, or less than or equal to 20. 4 plus 14 is 18, less than or equal to 20. Is that a true statement? It is, so it gets a little check mark. And then we can test equation 2. So 14 is greater than or equal to 4 plus 5. So 14 would be greater than or equal to 9, which is true. Okay, if you wanted to be safe, we could test another point. So we have 2, 12 is a solution. So let's see, 1 will have 2 plus 12 less than or equal to 20, and 12 greater than or equal to 2 plus 5. So 2 plus 12 is 14, which is 12 greater than 7. So there you go. So now you can do the worksheet on the real world problems. In the next video, there'll be one more short video. I will go over one of those problems in case you're stuck. We will also have a very short quiz on Tuesday on section 6.2. So just 6.2. So probably I'll ask you to graph one system of linear inequalities and solve one of these real-world problems. Okay, so there'll be one more short video, so make sure you watch that before Tuesday's class, and please email me if you're struggling with this at all.